SwayamPrabha. Digital India. Educated India.
Okay. So, in the last class we have been discussing about that beautiful diagram. I will draw it again and I have to draw many times. Reactor. I think by the end of this course you will all by heart this output, and it is not a bad diagram. Definitely if you remember this diagram you will know the entire picture of CRE, chemical reaction engineering, right. So, that is why you have to remember this. Okay, this is kinetics and here we have contacting. In kinetics we have again chemical and physical, and in contacting we have batch, continuous, and in continuous we have PF and MF. Okay. Yeah, I think PF means plug flow, MF means mixed flow, for those who are not familiar with this notation. Okay. So, then the performance equation is given by this: output is a function of kinetics, no, first input, yeah, input, kinetics and contacting. Yeah. So, this is the performance equation. Yeah, in fact, this tells that there are 4 variables. Okay. What we should know is kinetics, which gives you a rate expression. So, that is why it is no way different than biochemical reactor or normal chemical reactor, because if you are able to get a particular rate in biochemical reaction like Monod's rate, and they are very lucky, they have only 2 rates, right, either Monod's or Michaelis-Menten, right, and slight variations of that, in the denominator or numerator you add one term or remove one term, then you will get different forms of those 2 rates only. But whereas in the actual chemical engineering there are many forms of rates. Okay. So, you have this kinetics giving you a rate expression, a rate, and contacting will tell you what kind of reactor you have to choose. And fortunately for us we have only 3 reactors. 3 reactors. Okay. Yeah, 3 reactors. So, one is batch reactor and we have 2 continuous reactors, ideal reactors by name plug flow and mixed flow. If you are able to understand the meaning of this contacting, what is batch, what is plug flow, what is mixed flow, when do you use batch, when do you use continuous, that means lifelong you have all the information with respect to reactors. Only variation comes if they are not ideal, what is that you want to do, what is that extra information that comes into picture. Okay. That is why in my opinion contacting is much easier to understand and also to use all the time, whereas kinetics much difficult, right. And I do not know how many of you really understood what is the meaning of chemical and physical. What is the meaning of this chemical and physical? What did you write there? I think what do you mean by physical kinetics? What do you mean by chemical kinetics?
Reaction rate and mass transfer.
Who is talking? Okay. Reaction rate, right?
Mass transfer. Phase.
Yeah. Where does that come? Where does mass transfer come in chemical reaction rates?
Controlled by diffusion of the reactant.
Where do they diffuse? Where are? Yeah. Heterogeneous reactions. Right. In all heterogeneous reactions, you wrote very nicely that question. Everyone wrote uniformly right. Okay. Heterogeneous reactions and homogeneous reactions. What is the extra information we require in the heterogeneous reactions when compared to homogeneous reactions? That mass transfer, that is the extra step. Okay. But in fact, that is much more difficult, because for every reaction you have to first visualize how the reaction is taking place. That we will discuss a little bit later, but now first the contacting pattern is easiest. So, that is why I thought I will do first contacting, but before that, when you are writing an equation for either batch or continuous reactors, either this or this, we need a rate expression. So, that is why we have to now come back to kinetics again and then question this chemical and physical. These things will come in homogeneous and heterogeneous reactions, right. So, we can now divide these chemical reactions, now short form RXN, like action TV you have no AXN. So, like this here reaction, right, RXN means reaction. Okay. Now, chemical reactions can be divided into homogeneous and heterogeneous. Okay. Now, we have to identify homogeneous. How many phases we have? Homogeneous means what is the definition? You already know, you are experts. You should have one phase. Okay. Everything should be happening in one phase. So, how many phases we have? 3. So, shall I list all these 3 here? We have gas phase, okay, a gas phase, and then liquid and solid. Okay. Yeah, this is never called as homogeneous, right, because what is the meaning of homogeneous when you are talking in chemical reactions? For solid also the density remains constant.
No. Uniform concentration.
This is the problem, no, because we know only the definitions, but homogeneous we know, but I think beyond that when you ask, we do not get any answers most of the time. Okay. And what is that requirement in homogeneous reactions? Why do you say that okay, it is homogeneous? Homogeneous means single phase, but so what? In what is happening in that phase?
Reacting.
Reacting?
Molecules are atoms.
Molecules are?
Reacting.
Yeah, I mean everywhere, even heterogeneous also molecules are reacting. Otherwise, who will react? You will react, I am reacting. We react in a different way, that is different. Okay, molecules only definitely react. Okay, but still, why do you call it is homogeneous? Now, do not get disheartened. I mean, we are only just learning, so that is why you did not get. Next time, you should not say, no, this man is laughing, so that is why. No, no, I think it is only for joke. That is all. Yeah, molecules definitely react, but then actually, what is the requirement for homogeneous phase?
Properties should remain same. Like concentration.
Yeah, I mean, still, what is the meaning? Properties, yeah, okay, they are remaining same. So what?
So determining kinetics will be much more easy.
Why?
Because
Properties remaining
at
same.
At one location it will be different, and at some other location it will be different.
That comes as mixing, but I think yeah. Properties same means I think we are talking about concentration same throughout, but I think see the basic requirement in homogeneous phase is that the molecules should be readily available for reaction, right. So, that means if I have A and B together in a homogeneous phase, A need not search for B, B need not search for A, both of them are there very near. So, they come together and then collisions and all that we can imagine, no, then immediately you will get the reaction. So, that is why the basic requirement for homogeneous phase definition is that you have the molecules together and sufficient amount. Whenever A wants to react with B, B wants to react with A. It is not only that, many times you will have only A decomposing to some other reactions. So, that means all the A molecules should be just present there, and when you create this reaction environment, they should be able to easily react. That in the other sense, the molecules of a particular reactant in that phase should be freely available. There is no extra effort that is required for the reaction to take place, right. Okay. So, then that is what is the definition, and that cannot happen in solid phase. Okay. And even though if you take the purest form of solid, the molecules are not able to freely move. Okay. So, that is why this is a question mark always whether we have to call solid as homogeneous or heterogeneous. Okay? But most of the time you never get purest form of solid anywhere, right. So, that is why when the molecule wants to react with another molecule, that has to diffuse extra, okay, within the solid itself. So, that is the reason why when compared to liquid and gas, where the molecules are very free to move, I mean their kinetic velocities are 300 meters per second, 500 meters per second, and what is your diameter of the reactor? Maximum 3 meters, and that is moving 500 meters per second, the molecules, particularly gas phase. So, you see 500 meters means from here to your hostel in 1 second it goes. Can you go? If you are able to go when you are hungry, you may go. Okay, 1 second, half second also. So, that much faster, that means you can just imagine how easily they are available. Whereas solids, by definition they will not move, the molecules will not move. So, that is why you have to apply high temperatures, where more energy comes for the molecules, they try to move, and then that self diffusion is there. So, then other molecules will come together and then both will react. All that information is required, all those steps are required. So, that is the reason why normally we do not call them as homogeneous. That is why all the time we have gas and liquid as heterogeneous, homogeneous systems, where that means there is no effort extra required at all for the molecules to require, except temperature you are providing, sufficient concentrations you are providing, so that any time the reaction can occur. That is what is the definition of homogeneous reaction. So, I want to tell these basic things in a number of times. The reason is that those are the things which we have to understand. We know only the meaning of homogeneous, but beyond that, if you ask one more question, I think if you are not able to answer, means that is not the knowledge. That is only the parrot knowledge, where parrot repeats homogeneous, homogeneous, homogeneous 10 times. If you tell throughout its life, it will just repeat. If you ask the parrot, okay, tell me, explain what is the meaning of homogeneous, it cannot. So, we should not become parrots. No? So, that is the reason why extra information is required for us. So, the basic requirement for a homogeneous phase, when you say that I have a homogeneous reaction, is that absolutely there is no mass transfer limitation, molecules are freely able to move, and at any time if there are two A and B, these molecules are easily available to each other for the reaction to take place. Okay? So, that is what is homogeneous. And the heterogeneous, this we will remove now. We have more than one phase, right? Yeah. So, that means now we have totally 3 phases. The combination of all these 3 phases will give us the overall number of types of the overall types of reaction rates, reactions. Okay? So, I do not know whether you understood or not. We have 3 phases, combination of these 3, that means we have gas, liquid, solid, right, 3. So, first we will write here gas liquid is one combination, right, and then liquid is another combination, right, and then we have liquid solid is another combination. Yeah. So, then we have another combination is gas solid. Yeah. Come, I will come to that. Yeah. Okay. So, then so gas solid is another combination. Then what is the other one you are telling? Solid. Is there any other combination? Gas there is no combination, because gas molecules are so fast. Because I have written liquid, no. So, he is adding gas. We have now added liquid, gas and solid also. Okay? Yeah, gas is always homogeneous, because that is very free, happy to move. Okay? So, that is why that will not come. And gas, liquid, solid. Now, usually I will give the first exercise, first assignment is this. Now, find out under each category, under gas liquid reactions, heterogeneous system, minimum 5 actual reactions. You can't even tell one. Gas liquid systems, can you tell one reaction? Actual reaction I am talking about. See how much time we are thinking. Yeah, I know where to hit exactly. That is very bad. Okay. Now tell me, at least liquid liquid reactions, we do not know. At least liquid solid reactions, there are few which are easy for you to guess. Yeah, very good. Leaching most of the time, right. That means you take a solid, for example, if you want to remove purest form of copper, you take copper ore, add sulfuric acid or HCl, and then now you will have copper sulphate. I told copper, no. If you take sulfuric acid, copper sulphate, now you take copper sulphate to electrolytic cell and then separate SO4 and separate Cu, you will get the purest form of copper, which will get deposited on one of the cathode or anode. Okay. Yeah. So that is what I think you will have this one. Gas solid systems, many. This you should be able to tell. Burning of coal, copper oxide formation. Every day you see rusting. Yeah, rusting Fe plus O giving you FeO. Okay, you leave your cycle there, and before you go after MTech, you will see only rusted cycle. Most of you could have purchased good cycles, no? New cycles. Yeah, lock them properly. In IIT, all new cycles will go once, at least once. So that is why I think you buy more costlier than cycle keys, locks. Yeah, cycle now. How much is cycle now?
4,000.
My God. You know, when I joined here PhD, how much I have purchased? Can you guess? Good guess. 400. Just 400 I purchased. At that time also no thefts. Happy. Okay, no one was stealing our cycles. Cycles used to be there, but nowadays I think smart people, no. That is why what else they do. I think they are doing this kind of things. They think it is very smart. Okay, anyway, so rusting of iron and all that will come, but what you told, all these things, examples like coal combustion, carbon plus oxygen giving you CO2, I mean if you assume that only that reaction is present, all those reactions are called non-catalytic reactions. What is the difference? Both the reactants, carbon plus oxygen, both of them are participating in the reaction to give you CO2. But now you see, I will give an example. So that kind of even Fe solid plus O2 oxygen will give you 2 FeO. I mean that I will write now. I think I can write here C solid plus O2 gas. Better write these things. Earlier you are not writing the state of the reactant. So better write now, so that you will immediately know whether the system is homogeneous or heterogeneous, because you have now two phases. If I do not write S here, do not write G here, you do not know what is that. You do not know which phase they are. Of course, carbon and oxygen we know, but some other chemicals we do not know that. That is why better write that. If you do not know, you have to find out and write. This is CO2 gas. This is a non-catalytic reaction. And also I have Fe solid plus O2 gas giving us FeO solid. Correct, no? Yeah. So now it is balanced 2 2. Yeah. So that is one. And now the same Fe I can also use in other reaction. For example, N2 gas plus H2 gas. Yeah. Plus Fe solid giving us NH3 gas plus Fe solid, right? Yeah. So now I have to balance again this one. This is 2, this is 2, this is 3. What is the difference between this and this? Here also I have Fe, here also I have Fe. Yeah, here it is not actually participating in the reaction and getting transformed to something else, but it is retaining its iron form as it is, but only thing is it helps the rate of reaction to increase, right? Yeah. So that is why this is a catalytic reaction, this is catalytic reaction, and these two are non-catalytic reactions. non-catalytic reactions. Good, very nice. Yeah. So, this we have to first identify, because the design of catalytic reaction is totally different when compared to the design of non-catalytic reactions, right. But here catalyst is there. You have the packed bed, for example, that one of the examples we can give is packed bed. Ammonia, they always use packed beds only. All iron is loaded in this reactor, and then hydrogen and nitrogen, it is sent continuously. So, you will get continuous things, and most of the time this will not get deactivated. You have deactivation of catalyst. So, that is why for lifelong you can run that if you do not have deactivation. That is why packed beds are very good, in the sense that in packing, when you have packed beds, the solids are not moving. When you have movement of solids, then you have a lot of problems. Okay? How they move, where they move, and when they are moving, they are also rubbing towards the walls. So, after some time, 10 years if you run, walls may get eroded, thickness may go, then it may burst, all these things are there. But if they are not moving, happily sitting there, then that is why packed bed is called workhorse of chemical industry. Workhorse. You know, there are two types of horse: workhorse, running horse. Okay? Running horse will be useful where? Only in race courses. Okay? And they run only maybe how many minutes, I do not know, I have never gone there. Anyone has gone for races? No, nothing wrong, I say, to go and see also no problem. How many? One round, I think maybe 1 round or 10 rounds, I do not know how much, but maximum you take that, maximum half an hour it runs, and you know, preparation for half an hour run 1 year, good amount of food, some injections, many things they give. So, it is not profitable to industry, because we need a horse which will work all through, not that half an hour and then you know the remaining 395 days, not 365 days minus half an hour. So, it will be eating all the time. That is waste of time for us, waste of money. But we need work horses where all the time they work and in between they also eat, right. So, that is why the chemical industry, the packed bed, without any problems, all the time it works. That is why the name is given for packed beds as workhorse of chemical industry. Okay. So, that is a very nice name. Okay. So, that is why in the catalytic reaction what happens is the solids are there all the time, and you have to find out what is only the total amount of solids in the reactor. Okay. Based on that is why your design will be to find out what is the total amount of catalyst that is required. Whereas here I do not have Fe, at the end I do not have Fe, but it will become FeO. At least this is becoming a solid, but you see here I start with solid and I start with gas. Now, everything is gas. What volume you calculate? Is it solid volume or gas volume? Yeah, we will see, it is not gas volume. Okay. So, that is why the design of non-catalytic reactors and catalytic reactions is totally different, or reactors totally different. And now, we extend our definition, these are chemical reactions. The same thing is duplicated if I write here chemical reactors. That means, wherever these reactions are taking place, you can call them as heterogeneous chemical reactors, right. So, that means, I may have GL, gas liquid reactors, liquid reactors, liquid solid reactors, all combinations, and this one GLS is called as slurry reactor. Most of the time the solids are used in the form of slurry, and when you have liquid and put solids, and you do not put 1 kilometer, 2 kilometer diameters, okay, you will put only maybe 10 microns, 20 microns, 30 microns. You have the idea of microns? Yeah, how much? I do not have hair to say, but how much your hair thickness? 0.5 microns. So, that is why anyway, as engineers you better have that kind of estimation in the mind. It is excellent, what he has done is really good. We should have that kind of estimates. Like for example, if I ask what is the diameter of this pen? What is the diameter of this pen? Huh?
1 centimeter.
Yeah, 1 centimeter. Length?
12.
Yeah, maybe 10 to 12. Yeah, that means 6 inches almost. Okay, so like that, for example, when you are writing, the smokers cigarette, what is the diameter? Half centimeter. What is the length?
2 inches.
In fact, that is non-catalytic reaction. Correct? No, you are burning tobacco. Okay, and that is becoming like carbon becoming ash. Yeah, carbon also becomes ash if you have some other silica and all that. So this also becomes ash. No, every time you do like this, it falls. All that. Okay, so you can also calculate from non-catalytic reaction rates what is the time required for normal smoking of a cigarette. The normal smoking is simply taking and then taking one breath or so. But some people like for them the rate of reaction is very, very high. Why it is very, very high? No, not there is some step there. In fact, there is a mass transfer step coming. I don't know whether when I am doing like that, what I am trying to do? I am sucking the air. That oxygen will come through these pores because that is porous. You will not have solid cigarette. Solid cigarette means you cannot smoke will not come. You should be porous. And the beautiful question is, what is the porosity of a cigarette? Yeah, general knowledge. What will be the porosity?
4 into 10 power minus 6.
Unit size, meter cubed or kilometer cubed? Just guess. No guessing. Chemical engineering, no guessing. I think. Yeah, that will be around 50%. It is a packed bed, I say. Yeah, it is a packed bed simply. Because if you make the porosity 0.2, 0.1, your lungs will go much quicker. Anyway, they will go. Okay. It is only the time. It is only the time. Whether you choose 10 years or maybe 1 year. So that is why the design of, you see, for everything there is wonderful design. No? Really, for everything there is wonderful design. And also to stop all that nicotine and all that, they will have another filter on the top. Actually, that is bad for the lung. Okay, because it will extend your life a little bit, but lung will go because that porosity is small. The filter porosity, right? That may be only 0.2, 0.3 like that. So there you have to apply more pressure drop. The pressure drop across that is more. You see, all chemical engineering we are talking, even though we are talking about cigarettes. So every problem you can convert into as a chemical engineering problem, and then discuss about pressure drops, flow rates, mass transfer, all that. So that is why this person like that he is doing, that means he is taking a lot of oxygen, so burning rate is more, so cigarette is burnt very, very quickly, right. So that is why the design of non-catalytic reactions, not because of cigarette, when these two reactants are participating in the reaction, the design is different, whereas in this case the design is different. And this is also the reason why the rate of reaction is different here, the rate of reactions are different here. So for every reaction you have to find out rate of reaction for heterogeneous system. That is why I told you this portion is very, very difficult. Every reaction you have to derive an equation, whereas whatever reaction you bring, you have only 3 reactors. Correct? No? Any reaction you bring, any heterogeneous, homogeneous or all 3 phases, there nowadays biochemical engineers have actually 4 phases also. It is gas, liquid, liquid, solid. Okay. Yeah, someone was telling that this immediately when I wrote this, someone was telling that no sir, this is not correct, liquid is homogeneous. It is not homogeneous. Yes, it is homogeneous if the both liquids are thoroughly miscible. If they are not miscible, then definitely, like take for example kerosene and water or some oil and water. In this oil you have some reactant and water is another reactant, let us say. So now for the reaction to take place, the reactant in the oil should come to the surface interface. Okay. Similarly, from water side the reactant has to come, or water itself if it is the reactant, that has to contact that particular reactant which is in the oil. So, then only the reaction, that means what is that? That extra step. What is that extra step? Mass transfer. Not only mass transfer, even heat. So, heat and mass transfer both should be present. That is why we call this as physical reactions. I mean, physical steps that are required for chemical reactions. Because mass transfer is a chemical step, physical step, and reaction also, sorry, heat transfer also is a physical step. So, those are the two extra things that are required for heterogeneous reactions, for the reactor to be designed. That information you require. Why? Because that information only tells me what kind of rate expression I have. Whereas, in homogeneous reactions, what is the general rate expression? Just guess one, first order rate for example. Minus Ra equal to K into Ca. That Ca contains all the molecules. You have the concentration. How do you express concentration? Moles per unit volume. So, in that unit volume, how many moles are there? In 1 mole, how many molecules are there?
6.1.
That's all. So, that is the reason. But whereas that is not guaranteed in heterogeneous, the concentrations. Okay? So, that is why unless, okay, let me give you this example. I have this reaction carbon plus oxygen going to CO2. Okay, I keep carbon here and then next room we keep oxygen. Where is the reaction? It has to necessarily contact. That is why the term contacting has come. And this contacting is really very suitable for heterogeneous systems. Because in homogeneous there is no contacting in the sense that individual phases we are not contacting. But here you have many possibilities. How do you put gas liquid into the reactor? If it is batch, both you put and then wait. If it is continuous, because you can choose either continuous or gas, counter current, that is the only possibility. Why not co-current? Is that only possibility? Why not cross current? And beyond that we do not have any currents. Okay. So, all these things are possible. The moment you have co-current, counter current, cross current, your rate of reactions will change, your reactor design will change. That is why heterogeneous systems are very complicated. Heterogeneous rates are very complicated. But the beauty in chemical engineering is whatever contacting you use, cross current, counter current or co-current, the movement of that particular phase can be visualized as either plug flow or mixture flow. That is all. That is the beauty. That is really, my God, I will get really excited when I see the reactor design, because any kind of reactor you bring, even from other planets also or from our planet, we can reduce them to two continuous systems, either plug flow or mixture flow. But we have not yet discussed what is this plug flow and what is mixture flow yet. We will do that, right? So, but I have to talk to you about this kinetics first, so that we will have a meaning for the rate.
In heterogeneous reaction, in all these phases, we have heat transfer and mass transfer.
Yeah.
So all heterogeneous reactions are physical reactions.
No, because unless these molecules come together, chemical reaction happens. But before that, okay. Now again same example. Carbon I put there and oxygen I put this side. There is no contact, right? But what is the actual condition for the reaction to take place? I have to take the carbon lump, or this is the carbon. Over this we are sending oxygen, and fluid mechanics will tell me that whenever I have this kind of situation, because always we draw the spherical particles, even though there are not spherical particles, right? So then this goes like this. So this is oxygen, this is carbon, right? And fluid mechanics again tell me that whenever I have a solid and gas phase or liquid phase, around this solid we have what is called stagnant, place, which we call it as meter, which we call it as where is the vertex there? Not heard of, boundary layer is simply this is the boundary. Okay, that is a stagnant, stagnant layer what you said. Okay, stagnant layer is normal word, but boundary layer is high funda word. I think people will get impressed when you say boundary layer. So, now this boundary layer is stagnant. Now, you can say boundary layer is stagnant. Actually, that is not stagnant, it is dynamic, but because the oxygen molecules are just diffusing and CO2 molecules are, the oxygen is going out, CO2 also has to come. So, that is why again that is why you read Fick's law, counter current diffusion and all that. If correctly 1 mole is going inside and 1 mole is coming outside, then you have equimolar counter, and if you do not have that, then you have to go for that Stefan equation, correct, no, for multi component diffusion where the mole balance is not proper, all that. Okay. So, that is why that will become much more complicated. That is why we will say that okay, let us assume only equimolar counter diffusion. It is only because we are lazy to do that kind of mathematical work. So, we will assume many assumptions we make, so that our mathematics will be simpler, but we cannot make stupid assumptions. It should be realistic assumptions, where finally what your theory and what your experiment both are corresponding. That is what we have to do. So, now this is the one. So, here oxygen, as you said, even with the boundary layer, if there is not much oxygen diffusion to the surface, temperature is there, will the reaction take place? You will not have. If the oxygen concentration is very low, you may not have sufficient reaction. So, that is why the reaction between C and O2 is a chemical reaction. Oxygen molecule must be there and carbon should be there, then only the reaction takes place. But what is that physical step coming? This extra mass transfer step. Not only that, if I keep carbon we just store in the atmosphere, is it burning? It is not burning. Why? What is lacking there? Temperature. So, that is why heat transfer also is important. How do you heat this particle and you send very hot oxygen, okay, or air where oxygen is there, then initially it takes time for this particle to get heated up. That depends on thermal conductivity of carbon, correct, no? Yeah. So, then once it reaches sufficient temperature, then only it starts burning. That is why heat transfer is also a must step. Not only that, I think you can also take this catalytic reaction. Fe and nitrogen and hydrogen, these things will go to the reactor at what temperature? 350 or 550 degrees centigrade. How do you bring the catalyst to 550 degrees centigrade? Right? That is heat transfer. Unless all the particles are uniformly heated around that temperature, okay, you may not get uniform reaction rates. On the other hand, let us say that even this I have kept the reaction at 550 overall macroscopically, but now I will just look at one particular iron particle. Okay. What is the size they use normally? 2 to 5 meters. 2 to 5 centimeters. 2 means 1 inch, slightly less than 1 inch. Yeah. 2, 5. 5 means 2 inches. Yeah. Okay. Any other guess? I am not saying he is right or wrong. Huh? Less than half an inch. Yeah. Any other guess?
Powder.
Huh?
Powder form.
Powder form. Yeah. Any other? Powder means how much? So, because powder means anything can be powder, right? Yeah. Yeah, I think that is vague only. I think powder, anything can be powder. Even of course more than 1 mm we do not call powder. See, what is the talcum powder side which we apply for face? You should tell them. Nowadays they should also tell them. Because it is not only girls, boys also use. Yeah. How much you know? Yeah, general knowledge. What is your name? Gopinath. Yeah. Gopinath, any guess is there? Yeah, that is also 1 micron. Just imagine that you are applying that powder with 1 mm. Skin will come out when you are putting like this. So, 1 mm, that is why it is highly dangerous. You apply, maybe if you are taking 5 grams and then applying here, 2 grams will go inside, because you are not stopping your breathing and applying. You are breathing normally and then applying. So, when you put like this and then pour, something will go. That is why nanotechnology is highly dangerous technology. Really, they know that is a silent killer. Without knowing that you are doing nanotechnology, you may be knowing that you may be doing nanotechnology, but that will kill you depending on what kind of particles you are using. Those particles will happily go inside and deposit in the lungs and everywhere throughout the body. So, if they are toxic, then that is why there is a separate research going on how to estimate the toxicity in nanotechnology. I mean, we are very happy to write nanotechnology and also talk about nanotechnology, but these are the dangers there, right. Okay. So, normally the 2 centimeters to 5 centimeters normally no one will use. Normally it is half an inch, and particularly here ammonia they use. I asked I think why they use heat exchanger type reactor for ammonia. That is one of the questions which I asked in the first day question paper. You may not remember, I will remind you. Okay? Yeah, there is a special reason for that, which you will learn. Okay? So, they use heat exchanger type. That heat exchanger type means it is like heat exchanger where inside you have tubes, inside the tubes you have the packet beds, and those tubes are not normally more than 2 inches. When you have tube diameter itself for 2 inches, what should be the particle size? It may be 1/4 inch. Okay? Otherwise, if you use again big particles, you have what are called wall effects. You heard of wall effects. Okay? So, wall effects means when you have large particle and small diameter, your flow will not be uniform. So, that is why we say that it is wall effects and all that. That means your porosity inside that bed is not uniform. One particle this side, another particle this side, another particle this side, and when one particle is here, one particle is here, all this is vacant space. This is the diameter of the tube. So, that is the reason why that uniform flow will not be there. So, that is why wall effects, minimum number of particles you should put across the minimum across a diameter will be 8 to 10 particles. Okay? Along the length so many particles, all that I will tell you when you are coming to RTD and all that. I mean, these things will come there. Okay? So, all these things also we have to keep in mind when you are finally designing. So, yeah, what is that I was telling? I was telling about this iron where packet beds why do we use, and I think you asked a question for that. Who asked about that? Yeah, physical kinetics, I think I already explained that, because the physics, the 2 steps that I asked you that particle because that question, because I was telling you the entire reactor is at 550, but now I will take one particle out. Will this particle will have 550 or will it have different? Why different? Yeah, you are right, but why different? You see, this is what the thinking you have to do all the time, with your mind when you are thinking about any process. It is a metal, so I think conductivity is almost uniform, but it is not non-uniformity of the particles. There is a very good reason, whether it is exothermic reaction or endothermic reaction.
Heat of reaction.
Exothermic reaction. Okay? Where the reaction is taking place actually?
On the surface.
Why surface? It is a porous iron. You can also make porous iron. No? It is in fact porous iron, because we are not satisfied with only external surface. External surface is very small. Inside the surface, if I tell you, you will get really astonished. In some catalysts, even if I take 1 gram of catalyst, can you guess what is the surface area? Huh? Yeah, 200 meter square. That is minimum in fact. It can go to even 2400 meter square. In fact, we produced one, my PhD student, who was making activated carbon. In one sample, he got 2800 or 2700 meter square per gram of activated carbon. Okay? That means you can imagine this. What is the size of football ground? Olympics just now over. 2000 meters also you can tell.
100 meters in length and
100 meters, and then this one is
maybe 25, 30.
not more. if I remember correctly, that is I think 80, 160 or something, 80 meters and 160 meters. So, because its length is large, this is small. Yeah, how much if you multiply this? Oh, for easy calculation you can take 100 and
12,000, 1,000,
1000.
200 and
Okay, 2000. 2000 we can take, right? Yeah. And what is the catalyst per gram of catalyst? How much you can have? Good catalyst will have even 2000, 2400. This 200 is very very normal simple catalyst, and that is one of the objectives of chemical engineers, to produce as much surface area as possible. You don't have infinite opportunity to go for any area. Why? Because if you are putting more and more pores, then after some time everything will be pore, there is no solid. Okay, where is the particle? That means this mechanical strength of the solid will be, that is why you have to take into mechanical strength into account, and also what is the good surface area what you can get without sacrificing the mechanical strength. Why should I worry about mechanical strength? See, so many questions I say, I can talk, I am not able to start CRE. This is also CRE what you are talking. Why should I worry about mechanical strength, as if I don't have any?
Catalyst will run off with
Will run off with what? I am taking one particle size, I told you half an inch. How can they run off? And also they don't run off. You put a sieve at the top of the reactor, at the bottom and also top you put. On that only packed bed, all these solids are supported. You will have a perforated plate. Above that, if you are not confident, then you can put a sieve, and over that only you will keep all these catalysts. Top and bottom both places you put this. Why I should worry? Yeah, because in industry, in a one reactor you will have 2 tons, 3 tons of catalyst, and the bottommost layer should also withstand for that entire weight. It has to carry that entire weight. So, if it is not able to carry, what will happen? It will crush. When it is crushing, what will happen? You will have fine powder. It is good. When it is becoming fine powder, you will get very good surface area. That is very good. But problem is that will block all the pores. Then whatever compressor you use, it is not able to push. That is why we calculate pressure drop across the packed beds. What is the pressure drop that is required? When you have all powder, I think you or someone was telling powder. We can't use powders in packed beds because of this pressure drop limitation. When you put all the powder in a packed bed, then there is no porosity. When all of them are very fine powder you take and then pack, right? Then whatever compressor you use, the gas cannot go through that, and also you are fixing that between 2 good distributor plates, very fine distributor plates. If the distributor plate diameter is slightly larger than the diameter of the particle, then all the powder will come out. So, all these problems are there. That is why we take either 1/4 inch, 1/2 inch, that means maybe 12 mm, 10 mm, 8 mm, 6 mm, that is what the particles we use. But if the diameter of the particle is, reactor is slightly bigger, then normally we go for maximum 18 mm, that is 3/4 inch. Okay? 1 inch also, as far as I know in the industry, no one will go for catalysts, because we are losing surface area is one, but other than that also but we would like, mainly it is losing the surface area, right. So, that is the reason, and also as the diameter of the particle is increasing, we talked about mass transfer step, the particles, the gas has to diffuse into the particle. So, if you have bigger particle, then the diffusion is not very fast. When you have small particle, diffusion is very fast. That means through, you heard of effectiveness factors, right? Effective.
Big particle diffusion is difficult.
Yeah, the diameter of okay. If you are using this size particle, literally this size particle, so the gas molecules have diffused from here to here. So, the diffusion length is very very large, right. But whereas if I use 1 mm particle, the diffusion length is very small. So, that is why it is easy for the gas to diffuse, and that is why I asked you the question. You have heard of effectiveness factor, right? Yeah. So, what does that tell you? If I say that I have effectiveness factor equal to 1, what is the meaning of that? Yeah, but what is the condition in the particle? Right, what you said is right.
No resistance to diffusion.
Yeah. So that means throughout the particle I have the same concentration of bulk. That is the reason. So bulk concentration, that means practically this fellow is not allowing, offering any resistance at all. That is how you have to design your catalyst. It should be porous, but that pore should be sufficiently large. It should give sufficient surface area, but less resistance. That is why that idea of effectiveness factor. That is why you manufacture catalyst and then try to find out what is the effectiveness factor of the catalyst. So if I say that I have 50% only, that 0.5 effectiveness factor, we are talking about isothermal. Non-isothermal it will go much higher. Okay. So because same definition, you said the rate of reaction divided by rate at bulk conditions, right. So when I have highly exothermic reaction, the rate of reaction on the numerator is very high, but because the exothermic reaction, the temperature is more only inside the particle. So when the temperature is more, rate of reaction is more. So that rate of reaction and your bulk rate, where the temperature is less when compared to the particle, it is small. That is why you will have effectiveness factors more than 1 in non-isothermal case, but it should be only exothermic reactions. And in fact, I can tell you in the next semester you will get even 500 effectiveness factor, even 500. That means the rate of reaction inside the particle is 500 times larger than the rate based on bulk, which is very good for us. But again problems are there. If that is so much heat is generated inside, then the particle will get what is called thermal sintering, sintered. So when sintering occurs, naturally you will not have that effective sites, active sites of the catalyst, they will die. It becomes like glass surface. If it is becoming like smooth glass surface, then you will not have the defects where catalytic activity is going on. That is why we say that is called thermal sintering, and we also have the thermal deactivation. The other thing is called chemical deactivation. That means these fellows like sulfur and all that will go and then block all the active sites. And also even coal, when you burn, coke will form and that coke will completely block the surface where there is diffusion, but the actual catalytic surface is not available for oxygen to go and sit there, or some other component, active reactant to go and sit there. That is called chemical deactivation. You see how many things we have to think when you are designing heterogeneous catalytic reactors, whereas homogeneous homogeneous reactors, very simple. We have the liquid A and B, you put them together, make good mixing, they are miscible, 100% miscible. So then A is always finding B, B is always finding A. It is very easy to get married in the US, because A is available, B is available. One side, I will love you, I will love you, both go and then marry. Next day they may divorce, that is different. Okay. But that is very easy. But here our this procedure is very, very complicated, no. So the parents from boy side, parents from girl side, both have to meet, they have to high level discussions. Okay. Summit discussions they call. Okay. So those discussions, and now these parents will take another 5 people with them. These parents will take another 10 people with them, because girls will be always more careful. So that is why more people means proportional to more number of questions. So how is the boy and all that. So that is why it takes a lot of time for us. So that is mass transfer limitation. So reaction is not very fast. Okay. So but in the US, no parents, direct molecule stacking. Yes. Okay, happy to marry, happy to marry. Church is open, go there, get married, come out. Next day you may divorce and all, that is different. Okay, or they may stay together. So that is why, that is what is the you have to imagine for our molecules, that resistance only we have to remove. Okay, so that is why homogeneous reactions American society, heterogeneous reactions Indian society. Okay, good. You remember that, you will never forget what is the difference between these two. Okay, what I have to do in the next class is, I have to give actual definition of what is the rate, right. That means how do you define homogeneous rates? Okay. Actually rate is something per unit time, correct, no, anything from some unit time. right? Your speed also is rate, so many kilometers per second. But in chemical reactions, what we do is so many moles per second reacted, that is the rate. But always we use something else there. What is that? Volume. Why do you use that? Rate is simply only that. I would like to know only moles per time. So many moles have reacted, or vice versa, from stoichiometry you can say so many moles have been formed. Correct? No? I mean, left hand side, right hand side of the stoichiometric equation, if you see, so many reacted, so many formed. But I think always we can say in terms of reaction, rate of reaction. Oh yeah. Now tell me, why do you use that volume there? You said volume.
Is there and how much get reacted from that one?
Even without volume also I know how much reacted, depending on the rate.
That's a large number now, so
it can represent it in terms of concentration.
Concentration is always unit per, I can take 1 liter, and that means 1 mole per liter, 1 mole per liter. But why do you use this one for expressing the rate? See, these are all simple things where these are called cobwebs in the mind. We know rate, we know definition, but if you want to discuss further, we do not know. That means there are cobwebs, cobwebs you can see in the house. So, if you clear them, then you have the clarity in the house. Similarly, you have to also remove that cobwebs from our brain, then you will have clarity. That is why so much discussion I do. There is one very important reason why we do that. Okay? If I take 1 liter and 1 liter and react, my rate will be different. She takes 5 liters, her rate will be different. Okay? Because, okay? Yeah. So, like that you have different people now expressing different rates. If I take different concentrations, different volumes, then how do I simplify this? Because all of us should talk only one language. That is why you heard also in thermodynamics what are called extensive properties and intensive properties. What is the beauty with intensive properties? Independent of size. That is what we want to talk here. The rate is expressed like that, moles converted per unit time per unit volume. Then you take 10 liters, I take 5 liters, he will take 0.5 liters. All of us, when you convert per unit volume, we should get the same rate. That is the reason. That is the reason why we express moles per unit time per unit volume. Otherwise, I may say that okay, my rate is 100 moles per second. He will say that my rate is only 0.1 mole per second. It is same reaction. Right? So, that is why the definition of rate of reaction is very important because of that reason. Right? And now the same thing if I extend for heterogeneous systems, now this volume is there. That volume is what? Homogeneous reactions I am talking. That moles per unit time per unit volume. What is that volume? Volume of reaction mixture where both are miscible, right? If it is liquid or gas, and we are talking about that volume. Right? And now, if I take this liquid, they are not miscible. Simplest example. So, then how do I express that rate? Sorry?
In terms of surface area.
In terms of surface area. That is the only way. So, that is why there are many possibilities for heterogeneous systems. That is right. Very good thing is to express based on surface area. Why? That is where the actual reaction is taking place. But you know how difficult it is to estimate correctly the surface area, particularly in a large column where I have two liquids. One is called dispersed phase, because you are dispersing, you cannot have two continuous phases. So, your limitation of contact is very, very low when I have two liquid, two continuous phases. That is why we disperse one liquid into other. We will make very, very fine droplets of one liquid into other. Why? These fine droplets will give me lot of interfacial area. That is why I told you, some time back, chemical engineering definition is that it is bubbles, drops and particles. If you are able to really understand the behavior of all these three, okay, and combinations, then you know all chemical engineering. So, that is why what we do is, okay, it is very difficult to find out what is the interfacial area. Let me find out at least volume of one reactant. That we know, I am charging. Or otherwise, you say why one reactant, sir, why not two reactants? Yes, no problem. Or you may say that why only 1 2 reactant volumes, let me take weights. So, I will say that moles converted per unit weight of the liquid, both the liquids together or one liquid together, maybe continuous liquid, continuous phase. So, that is why you have many possibilities to define the rates. That is where the confusion starts when you are designing heterogeneous reactors. The definition itself is not clear. You should have seen the design of catalytic reactors, right? So, definitely some of you, right. So, then what is the rate? How they express the rate? Weight of catalyst. Is it the only way? Need not be. You can express surface area of the catalyst, but again it is very difficult to find out surface area, because there are 2 surface areas for a catalyst. What are the 2 surface areas? One is the external, the other one is all together, external plus internal together. Which surface area you are talking? What you measure using BET method, no? BET method or some mercury porosimeters, what you measure is the entire surface area of the particle inside the pores, outside surface, all together you estimate. Estimation is again difficult. That is why the simplest parameter which I can use is weight of the catalyst, because I can simply put weight 10 kgs, 20 kgs or 1 kg, and then find out the rate based on weight and use the same rate, so that you will get weight of the catalyst in the actual reactor. That is why the reactor design, whatever you express the rate of reaction on, that means you can express as volume of reactor, weight of reactor, I am sorry, weight of catalyst or weight of surface area, you will get directly in the final, when you are going for this design equation, you will get that particular part. If I use my rate based on weight of the catalyst, I will get weight of the catalyst. If I use my rate based on volume of the catalyst, I will get volume of the catalyst. But this volume of the catalyst, again there are many misconceptions there. What volume we are talking? Volume of the catalyst means this volume has the catalyst has inside again void volume. Are you talking about only pure solid volume, or that means everything crushed together and then you will have no pores at all? Are you talking about that, or are we talking about the volume of the particle, or you are talking about the volume of the reactor? Correct, no? Reactor has now additional voidage. Packed bed, you have the particles, this particle is porous, some void volume there. So, now all these particles are kept in a reactor, where you have between the particles there is some more void volume. Which volume we are talking? That is why we have to clearly say, okay, moles converted per volume of the reactor, that means you are talking about the entire reactor, or volume of solid, or volume of solid, that means without any voids. Okay? Yeah. So, like that only, or volume of voids only, Which voids again? Reactor voids or particle voids. You see how much confusion is there. That is why we should have very clear picture of what we are talking when you are talking about heterogeneous rates.